Hi, this is Kai Wang from University of Southern California. Today my presentation is deep learning detection of penumbral tissue on arterial spin labeling in stroke. I have nothing to declare. When the acute ischemic stroke happens, the ischemic core is where the ischemia originates. Therefore, brain tissue of this region is non-salvageable, and the larger region around it is the hypoperfusion lesion, which includes the ischemic core and the penumbra. The penumbra is most likely to benefit from endovascular thrombectomy treatment. Imaging criteria for endovascular thrombectomy of diffuse 3 trial includes the volume of ischemic core is smaller than 70 milliliter. The volume of hypoperfusion lesion is larger than 1.8 times the volume of ischemic core, and the penumbral volume is larger than 15 milliliter. Clinically, to identify the ischemic core, usually the diffusion-weighted image DWI is used, and to identify the hypoperfusion lesion, the dynamic susceptibility contrast enhanced DSC MRI is usually used. However, it is gadolinium based, so it brings risk to some patients. On the other hand, the arterial spin labeling ASL MRI is totally non-invasive with no exogenous contrast needed. It provides CBF measurements, which provides largely consistent results with DSC in delineating hypoperfusion lesion in acute ischemic stroke patients. However, precise hypoperfusion lesion and penumbra delineation in ASL images is still challenging due to the low SNR and delayed arterial transit of ASL. Therefore, we want to propose a deep learning model that was trained on ASL and DWI images and DSC perfusion images with the aim of aiding endovascular thrombectomy decision-making. Here is the flowchart of our experiment. We have the data input of CBF, ADC, and Tmax, which were used to train the deep neural network. Then the results were evaluated by a voxel level evaluation and subject level evaluation. And in terms of participants, two cohorts were included, the UCLA cohort and the Stanford cohort. The UCLA cohort includes 167 image datasets acquired on Siemens 1.5T and 3T. And the Stanford cohort were acquired with GE 1.5T and 3T. Details about image acquisition and pre-processing can be found in the paper we already published. Specifically, the CBF was acquired with 3D pseudo-continuous ASL sequence, and the label was generated from Tmax with skull stripping, CSF masking, thresholding by 6 seconds, and morphological cleaning. This is the structure of the deep neural network we used. It's a high-res 3D net with 20 trainable layers and dilated convolution. The volume size is 48 by 48 by 48. Batch size is 4 with volume level data augmentation. We used dice loss and Adam optimizer, and tenfold cross-validation was used. To provide benchmark for performance assessment, 6 traditional machine learning models were also trained, and the performance of the deep learning model and the machine learning models were compared. As for the performance evaluation, it was done on a subset of UCLA cohort with 38 subjects, and the evaluation includes the voxel level evaluation and subject level evaluation. For the voxel level evaluation, we calculated the Dice coefficient for each subject, and we calculated the ROC curve. And for the subject level evaluation was based on the imaging criteria of diffuse 3 trial. The treatment decision was made based on the ground truth and the inference. Then by comparing the two, we get the confusion matrix and the total accuracy calculation. To evaluate the generalizability of our deep learning model, our deep learning model was tested on Stanford cohort, which came from a different site and a different platform without any parameter fine-tuning. And then both the voxel level and subject level evaluation were performed. As for the voxel level evaluation, here's the ROC curve for both UCLA cohort and Stanford cohort. Our deep learning model achieved the AUC of 0.96, significantly larger than any of the 6 other machine learning models. And on the group average dice is 0.47 plus minus 0.23. On the Stanford cohort, the AUC of the deep learning model was 0.94, and the group average dice is 0.43 plus minus 0.25. As for the subject level evaluation, our deep learning model achieved high accuracy of 0.92 on the UCLA cohort, with 95% CI from 0.79 to 0.98. And in comparison, the highest accuracy among the 6 machine learning models was only 0.84. And our deep learning model achieved the accuracy of 0.92 on the Stanford cohort, with only 1 subject misclassified. Here we showed some representative cases from both UCLA cohort and Stanford cohort. And 4 representative cases, 4 cases were shown for each of the field strength for UCLA cohort. Only this subject was misclassified. And as for the Stanford cohort, only the 3rd one was misclassified, which is also the only one that was misclassified in the whole cohort. The arrow indicates the hyperperfusion signal likely arising from delayed arterial transit effects. In conclusion, our deep learning model can achieve high accuracy of 0.92 in 2 independent cohorts of AIS patients. It showed superior performance compared to the other machine learning models, and therefore the proposed ASL perfusion deep learning model may provide a promising approach for assisting decision-making for endovascular treatment in AIS patients. And further possible improvements can be made with larger data set and other clinical information and fine-tuning parameter for other separate data sets. I want to thank my colleague at USC and our collaborators from Stanford and UCLA and NIH grant support. Thank you.